Audio Jungle.
Do you wonder how Indo-Arabic numerals originated? Do you have any idea what's the prominent to use negative numbers? How about renowned people who represent fractions as decimals? Do you know that there was a mathematician who proved binomial theory by induction prior to Blaise Pascal during 17th century? We are often attracted to designs that involve geometric properties, but overwhelming people prospering these ideas. Most of all, was the famous mathematician who acknowledged the presence of the unknown and later developed one of the comprehensive branch of mathematics, the algebra. These are important questions that will lead us to explore a significant era in the development of mathematics, the so-called Islamic Mathematics. Islamic mathematics is a term used to refer to the mathematics done in the Islamic world between the 8th and 38th century CE. Mathematics from this Middle East is very important to the mathematics we use today. While Europe endured its dark ages, the Middle East preserved and expanded the arithmetic, geometry, trigonometry, and astronomy from the ancient Greek philosophers such as Euclid. The most important contribution may be the invention of algebra, which originated in Baghdad in the House of Wisdom.
The House of Wisdom was primarily a library and a place for translation and research. Scholars would work here in translating Greek and Hindu treatises to Arabic, and also conducted their own research and wrote original treatises. The House of Wisdom was established in the early 9th century, by Caliph al-Rashid. His son, Caliph al-Ma'mun, was the ruler who made the House of Wisdom so important. Al-Ma'mun had a dream in which Aristotle appeared to him. After this dream, al-Ma'mun wanted to translate as many Greek manuscripts as he could. He commissioned scholars to begin translating Greek, Hindu, Syriac Persian, and Hebrew texts into Arabic. Most of these texts dealt with philosophy or mathematics and science.
Muhammad ibn Musa al-Khwarizmi, or also known as al-Khwarizmi, a Persian polymath from Khorasan, who produced vastly influential works in mathematics, astronomy, and geography. Around 820 CE, he was appointed as an astronomer and head of the library of the House of Wisdom in Baghdad. Al-Khwarizmi's popularizing treatise on algebra, the compendious book on calculation by completion and balancing, presented the first systematic solution of linear and quadratic equations. One of his principal achievements in algebra was his demonstration of how to solve quadratic equation by completing the square, for which he provided geometric justifications. Because he was the first to treat algebra as an independent discipline and introduce the method of reduction and balancing, the transposition of subtracted terms to the other side of the equations, that is, the cancellation of like terms on opposite sides of the equation. He has been described as the father or founder of algebra. The term algebra itself comes from the title of his book, the word aljabar, meaning completion or rejoining. His name gave rise to the term of algorithm and algorithm, both meaning digit. Al-Khwarizmi wrote a treatise entitled Kitab al-Jabar wal Muqabala The treatise actually had a very practical reason behind it. The longest chapter of the treatise teaches people how to apply algebra to Islamic inheritance laws. The words Al-Jabr and Al-Muqabala were operations used by Al-Khwarizmi, much like addition, subtraction, multiplication, and division. Al-Jabr means something like restoration or completion, and was the operation used to add equal terms to both sides of the equation to get rid of a negative term. For example, with the equation x squared equals 40x minus 4x squared, Al-Khwarizmi uses algebra to add 4x squared to both sides of the equation, getting the result 5x squared equals 40x. He can then complete the problem by division, dividing 5 both sides, then x squared equals 8x, and dividing x both sides leads to x equals to 8. Though we know that x equals to 0 and 8, Al-Khwarizmi never allows a variable to equal 0. Al-Muqabala means something like balancing, and was the operation used to subtract equal terms from both sides of an equation. For example, Al-Khwarizmi has the equation 50 plus x squared equals 29 plus 10x. So he uses Al-Muqabala to subtract 29 from each side, getting the result as 21 plus x squared equals 10x. From here, Al-Khwarizmi can then complete the problem, x squared minus 10x plus 21 equal to 0, by factoring x minus 7 times the quantity x minus 3 equal to 0. By the principle of zero product, x will be equal to 3 and 7. As you can see, Al-Muqabala and Al-Jabr were operation defined by Al-Khwarizmi, which we still use today, though we don't call them the same thing. This operation Al-Jabr, adding equal amounts to both sides of the equation, is where our algebra comes from. Al-Khwarizmi also created the method that we now call completing the square. However, Al-Khwarizmi literally completed the square. If he had an equation x squared plus 10x equals 39, Al-Khwarizmi would create the following figure. First, he would make a small square with each side length equal to x. This square then has an area of 39 minus 10x. Then he added on rectangles to each side of the square, each with a width of 10 over 4 or equivalent to 2.5. Note that the area of the rectangle is given by the formula length times width, and since the equation can be written as x squared plus 10x equals 39, can be seen that the area of the square and the 4 rectangles added to 4 corners of the square is equal to 39. That is, x squared plus 10x equals 39. The area of the 4 rectangles therefore is 10x. Since the length is x, it follows that the width is 10 over 4 or 2.5. Completing the figure to make a large square with the corner squares with sides equal to 2.5, he then had the figure to use to find x. Therefore, the area of the large square with the side equal to x plus 5 is equal to the shaded region plus the area of each corner of the square. That is, the square of x plus 5 equals 64. Taking square root both sides could lead to x plus 5 equals 8 or negative 8. Therefore, by Al-Muqabala, x is equals to 3 or negative 13. Al-Khwarizmi also provides a second way to complete the square, which might be easier for modern algebra students to use. Using the same equation x squared plus 10x equals 39, he creates the following figure. First, we make the square with the sides equals to x. Again, the area of this square is x squared equals 39 minus 10x. Then, he added on rectangles with the lengths turn over 2, which is equals to 5, to both sides of the given square, having the sides which is equals to x. So the area of this figure is equal to 39. In other words, x squared plus 2 times the quantity 5x is the same as x squared plus 10x, which is equals to 39. You then complete the figure to make a large square by finishing the square with the sides of the length equal to 5, which give the figure that can be used to find x. Then Al-Khwarizmi uses the same method to use above to get the area of the completed large square with the side x plus 5, and that is the quantity x squared plus 10x plus 5 squared is equals to 39 plus 25, and that is equals to x plus 5 squared equals 64, and he gets the same result as he did in the previous example of completing the square, that is x plus 5 is equals to 8 and negative 8. By Al-Mukabala, x equals 3 or negative 30. So when we talk about completing the square, when we solve quadratic equations, we refer to the method of Al-Khwarizmi, which literally created and completed the square to find the value of x. With the remarkable idea of unknowns profoundly used by Al-Khwarizmi, another breakthrough of Islamic mathematics shined when binomial theorem being proved before Blaise Pascal in 16th century. The famous mathematician is the first ever known to use mathematical induction to prove this theorem. He is the great Al-Karaji.
Abu Bakr ibn Muhammad ibn al-Husayn al-Karaji, or mostly known as al-Karaji, born 953 CE, died around 1029 CE, was a Persian mathematician and engineer, who has made massive contributions to the development of 10th century mathematics, particularly in the field of binomial theorem. Al-Karaji successfully dealt with the algebra of powers higher than 2. He gave the following names to the higher degree algebras. Al-Karaji then noted that these higher degree terms polynomials may be treated exactly like the digits of a multi-digit number. He then proceeded to prove that 3x6 plus 2x6 equals 5x6, by adding up the coefficients, and doing the same with subtraction of one polynomial with the other, 3x6 2x6 equals x, by subtracting the coefficients of the polynomials. Note that Al-Karaji's work portrays a simple but extremely important conclusion that polynomial expressions could be added, subtracted, multiplied, and divided, using the same algorithms applied to operations with numbers, without any reference to geometry. Another remarkable contribution of Al-Karaji made is in the development of binomial theorem. Al-Karaji dealt with the problem of expanding binomials that are being raised by an exponent greater than 2. The binomial a and b, 2 is relatively easy to expand, to get a2 plus 2ab plus b2, but as we go higher up, the work will get more and more tedious. Say, for example, to expand the binomial a and b, 6. Al-Karaji tried to deal with this problem by constructing a structure similar to the famous Pascal's triangle. In fact, we may assert that Karaji's table is a pioneer to the Pascal's triangle. In order to figure out the binomial coefficient as we go higher up the power of a binomial, the table is extremely useful in finding the binomial coefficient of higher degree binomials. For example, if one wishes to find the binomial coefficient of a and b raised to 4, from the table we know that they are 1, 4, 6, 4, and 1. Using this, we may get the entire expanded binomial, with a few extra tricks that will not be explained here, as with 1, 4, 6, 4, and 1 as the binomial coefficient of this expanded binomial raised to the power 4. This marks a new development in binomial theorem in mathematics. The last contribution of Al-Karaji that will be mentioned in this write-up is that Al-Karaji was among the first mathematicians who employed the method of mathematical induction as proof to his theorem, apart from the Greek philosopher Plato, 428 BC 348 BC, and the Greek father of geometry, Euclid, mid-century 4th century BC mid-century 3rd century BC. Using mathematical induction as proof, Al-Karaji proved that the sum of the first natural numbers was n over 2 times the quantity n plus 1. The sum of the squares of the numbers that follow one another in natural order from 1 is equal to the sum of these numbers and the product of each of them by its predecessor. The contributions of Al-Karaji to the world of mathematics in general and economics in particular are both astonishing, inspiring and spectacular. Without his works, mathematics may not be as how it is, and our learning progress in economics may be seriously hampered.
Ibrahim ibn Sinan, dated 946, is the grandson of Thabit ibn Qurra, the famous mathematician and translator of Archimedes. His treatment of the area of a segment of a parabola is the simplest construction from the time before the Renaissance. He wrote that he invented the proof out of necessity to save his family scientific reputation after hearing accusations that his grandfather's method was too long-winded. He also was more concerned with general methods and theories than with particular problems. Ibn Sinan describes the following method for drawing a parabola. First, draw a line AG, create a fixed segment AB on AG, and construct BA perpendicular to AB. On BG, pick as many points H, T, Z as you want. Starting with the point H, create a circle with diameter AH and let the perpendicular BA intersect it at T. Through T, create a line parallel to AB, and through H, draw a line parallel to DE. These lines intersect at K. Now draw a circle with diameter AD and let this intersect DE at I. Following the same procedure, draw a line through I parallel to AG and a line through D parallel to BE. Let these lines intersect at L. Follow the same construction method for the remaining points Z to obtain the corresponding intersection points M. Then these points B, K, L, and M lie on the parabola with vertex P, axis BG, and parameter AB. Create K prime, L prime, and M prime on the extension of the lines KH, LD, MZ so that KH will be equal to HK, LD congruent to DL prime, and MZ congruent to ZM prime. Then these points K prime, L prime, M prime also lie on the parabola. Ibn Sinan applies the same proof to L and M to prove the validity of his parabolic construction. This method shows the ability of Ibn Sinan and Muslim mathematicians to construct a proof in the style of the Greeks, as well as their contributions to geometry by providing more concise geometrical constructions and proofs.
More than 1,000 years ago, Muslim scholars and artists, especially in the Baghdad area, created an alternative form of decoration using only the basic tools of Euclid, namely the compass and the straight edge. We call them Islamic geometric patterns because they have a lot of mathematics in the structure. Still, geometric designs were used significantly in Islamic art. Actually, not only in Islamic art, Islamic geometric art was of significant assistance to Dutch artist Maurits Cornelis Escher, who is famous for his optical illusions of ascending and descending stairs, metamorphosis, and reptiles. Since the depiction of humans and animal figures is not part of Islamic culture, Muslim artists used geometrical shapes and calligraphy to make repeated patterns as a form of decorative art. Islamic geometric design was a tradition, but in reality, these geometric patterns are pieces of art, the art of architecture. Muslim artists have been adorning mosques, palaces, and books with their geometric patterns and calligraphy work since the 8th century. We mostly see the Islamic geometric patterns in places of worship are used as a medium to glorify God. The grand structures such as buildings, gardens, floors composed of divine geometry.
Tabit ibn Qura. The 9th century Arab Tabit ibn Qura, who developed a general formula by which amicable numbers could be derived, discovered much later by both Fermat and Descartes. For example, the proper divisor of 220 are the following numbers, and the sum of this proper divisor is 284. Moreover, the proper divisor of 284 itself are the following numbers, and the sum of this proper divisor is 284 also. Therefore, we can say that 220 and 284 are amicable numbers. This was created by Arab Tabit ibn Qura. Abul Hasan al-Oqlidisi, 10th century mathematician, who wrote the earliest surviving text showing the positional use of Arabic numerals, and particularly the use of decimals instead of fraction. For example, 7.375 instead of 73/8. Ibn al-Haytham, 10th century mathematician, also known as Al-Hasid, who in addition to his groundbreaking work on optics and physics, established the beginnings of the link between algebra and geometry, and devised what is now known as Al-Hasan's problem. He was the first mathematician to derive the formula for the sum of the fourth powers using a method that is readily generalizable. Kamal al-Din al-Farisi, who applied the theory of conic sections to solve optical problems, as well as pursuing work in number theory such as on amicable numbers, factorization, and combinatorial methods. Ibn al-Bana al-Marakushi, whose works included topics such as computing square roots and the theory of continued fractions, as well as the discovery of the first new pair of amicable number since ancient times. For example, 17,296 and 18,416, later rediscovered by Fermat, and the first use of algebraic notation since Brahmagupta. With the stifling influence of the Turkish Ottoman Empire from the 48th or 50th century onwards, Islamic mathematics stagnated and further developments moved to Europe. And that is all about Islamic mathematics. Hopefully we learn a lot of this video, and as a math-inclined learners, we will always instill and give importance to the contributions of Islamic mathematics.